everyone, welcome to our lesson on polynomial functions. Remember, our polynomial functions are those expressions with many terms, and there are lots of characteristics we can talk about to go along with these polynomial functions. So once we get to our picture that is graphed, we'll talk about those. Polynomials are called polynomial functions because of the prefix poly, meaning many. It could still just be one term, or it could be many when you see them. Something that is very important to look at is the degree and leading coefficient. Once you're in standard form, which is ordered from greatest to least by power, you can clearly see the degree and leading coefficient in the front. That will be in the very front term. Degree is going to be the power that's attached, and the leading coefficient is the number in front. Alright, so let's take a look at an example of a polynomial. And one other thing to note about polynomials is that you are only looking at a polynomial if you are looking at something with all the exponents being whole numbers and all the coefficients being real numbers. If you ever see an I that is sneaking in there, or a negative power, you're not looking at a polynomial. So we have to first make sure what we're looking at is a polynomial. And then a good place to start is to put the polynomial in standard form. So we said that is ordering it from greatest to least by power. So if I take a look at this one, I'm going to go with the x to the 5th power first, 8x to the 5th. Second highest power is here, the cubic power. Just going to switch them around a little bit, and then third highest, 4x squared, and then my constant term. And once we're in standard form, remember the degree is going to be the highest power that you see, which will now be in front, and the leading coefficient is the number in front of that term. So we have a polynomial of degree 5 and a leading coefficient of 8. I'm going to fill that in here. Alright, some other characteristics of polynomials. You can use many different methods to factor and find the zeros. But one thing to note is that the polynomial will have as many zeros as its degree number. So the one we just took a look at had a degree of 5, so it should have 5 of some kind of zeros. They may be any combination of real or imaginary zeros. Also, since it has that amount of zeros, it will have one less turning point, meaning the times that it changes direction on the picture. Alright. To determine what's going to happen at the very ends of the polynomial, we're going to take a look at that same thing, the degree and leading coefficient. And here's the pattern here. If we have an odd degree and we notice that our leading coefficient is positive, then our left end is going to be down and the right end is going to be up. Okay. If we notice that we have an odd degree but it's negative leading coefficient, the left end will be up and the right end down. Okay, we're talking about the very ends, not the stuff in the middle. And then if we have even positive, they're both up. Even negative, they're both going to be down. So we'll kind of keep that pattern in the back of our minds as we graph. So let's take a look at one to graph. To get a really accurate picture, you can always test some x values and find the matching y's. You can test as many as you want to get a clearer picture. But if you can remember the basic characteristics that we've discussed, you can get a pretty good general picture just from those things. So, for instance, we looked at the patterns of end behavior. If we notice that we have a degree 3 and that it's positive as our leading coefficient, remember that is an odd positive. Going back to our patterns, odd positive, the left end should be down and the right end should be up. So when we finished, it should do something like this. Again, we don't know what's happening in the middle, but the ends are doing these things. And like I said, we can test some points, any amount of points that we want to, plugging in those numbers for x and finding matching y's. So just a couple here, a couple easy numbers. If I plugged in a 0, all I would be left with is 3, so we know it goes through this point. And just testing one other. You were to calculate in a 2 cubed minus 3 times 2 squared, and continue that out in the correct order, you will get a matching y of -3. Here's just a couple of XY pairs we can put in there. And then another really nice thing to find are the zeros. There's different methods for that, synthetic division or factoring if possible. We've already found the zeros of this one. They are 1, -1, and 3. So remembering all these things, we can get a pretty good general picture. So let's take a look. Starting with our zeros. We're going to plot those first. So go put you some points on 1, -1, and 3. Remember we said the end behavior, we want the left end to be down and the right end up. So we're going to be coming in from the left here and crossing through this 0. Now we tested a couple points. We tested 0 and we got 3. So we know it's going to at least go up through this point here. And then we also tested the point 2, or the x value 2, and we got a matching y of -3. Go plot that one. We know the picture is going to come down. It's going to have to cross through this 0 before it goes down to this point. Then we're not really sure exactly how far it goes down. We didn't test every number in between these zeros, but we do know eventually it will come back up and it must cross through that point as well because that is a 0. So there's a really good general picture. All right, let's list some things based off of our picture that we can notice here. Remember the zeros? We already found those. Places where it crosses the x-axis, the x-intercepts were -1, 1, and 3. So we'll list those out. A term you might come across in looking at these polynomials is the intervals of increase and decrease, and that's simply just where the picture is going up and where it's going down. Coming in from the left like you would read a book, if I start on the left end, it starts off going up until we get somewhere around the point that we tested. Now remember, we did not test every point in between these zeros, but let's go with this picture for listing the characteristics. Let's say that is the max point there. Here I can see it turns, changes directions, goes back down, and then down here at this point of 2, -3, it turns again. So my intervals of increase, I can see 2. I've got the one coming in from -infinity all the way to 0. The x value there is 0. And then another one starting at the x value of 2 and going to infinity. So one way we can list these are using our interval notation. One was -infinity to 0 and one was 2 to infinity. Okay? 2 intervals there. All right? And it was decreasing in the middle. It was traveling down the middle of those two. So from 0 to 2. We can use interval notation for that as well. Just writing these above these words here. Our end behavior is down and then up. So the formal math notation for that is as x approaches -infinity, that means the left-hand end, the function was down. So f of x approaches -infinity as well. And on the right-hand end, as x approaches +infinity, that just means out to the right, the function was up. So f of x was also +infinity. So that's the formal way that you can state those. Domain is another term you may come across, domain and range, when talking about characteristics of graphs. Domain just simply means what x values is your picture covering. Well, we can see that there are arrows on both ends. Polynomials will continue on forever. And we're slightly moving down, slightly left, but we'll eventually hit all the x numbers to the left and all the x numbers to the right. So we're covering all real numbers. So you can say all reals, or you can use your interval notation again, -infinity to +infinity. And the range, the y direction, the y numbers that we're covering is actually going to be the same thing here. Because we have one end down and one end up, that means we're going to eventually cover all y numbers as well. So, all real numbers, also known as -infinity to +infinity. And this concludes our lesson on polynomial functions.